Hi. So what do we mean by the simple geometric interpretation? Consider a segment of a beam or a line which is of unit length to be divided into two unequal parts, x, and therefore by definition 1 minus x, right? Then take one leg of the unit length and divide it. Take that part, that is x upon x minus 1. We assume x is longer than x minus 1. So it's the ratio of the longer by shorter part. This can also be written as 1 by. Such an equation results in a solution that is a quadratic equation with a unique positive solution which goes as this. That is x is equal to under root 5 minus 1 by 2. And that is equal to 0.618. From algebra, we can show that 1 by x is equal to 2 upon root 5 minus 1, obvious, is equal to 1 upon root 5 by 2 is equal to phi. So we come back to our phi, our golden number. Since phi is a unique real number, when the division of a line is concatenated, it results in a constant. This is nothing but what we saw with the Fibonacci series and the ratios. Therefore, phi is also then called the golden ratio. It is found in many architectural and cultural artifacts. And it's thought to have some significance. But for us, the significance is really focused on Phyllotaxis. Many identities come from phi. So it can be shown that phi into phi minus 1 is equal to 1. We do this as 4. And the length x and one minus x can be expressed in terms of phi. such as x is equal to 1 by 5, 1 minus x is equal to 1 minus 1 by 5, which is equal to 5 minus 1 upon 5, which is equal to 1 by 5 square. This we obtain from here to here by substituting the equation 4, which is here. Thus, x is equal to 0.618 by substitution. Phi is equal to 1.618 and 1 minus x is equal to 0.382. These numbers show up again, so I'm just going to highlight them, keep them in mind. The second part is the golden angle that in a way builds on the geometric interpretation. We take into account a circle and divide it again into two parts. So I'm going to draw this by hand. I'm afraid it's not going to be very good. Yeah. This segment and the other segment. The other segment we call x, the longer one, and 1 minus x. That's the shorter one. The circumference is 1. That's the working assumption. Perimeter. The lengths, therefore, of the two segments are indeed x and 1 minus x. By definition, from what we did earlier, this can be written in terms of 1 by 5 square, and this as 1 by 5. So in that sense, the lengths are now related to phi, the golden number. We want to know the angles. So in case of Phyllotaxis, if the organs are at 2 points, then the angular distance is 180 degrees. We can say there's a half turn corresponding to 180 degrees. If on the other hand we have 3 organs, then we are referring to an angle of 120 degrees of equal 1 by 3. And similarly, in the case of a 4-organ structure of equally spaced organs, we end up with 90 degree angles. So the fraction of the turn of a small portion of the perimeter measures the golden angle. So this angle, gamma, is the one we're interested in. The fraction of the turn of the small segment, 1 minus x, which also has perimeter, therefore 1 by phi squared, measures the golden angle gamma, which is equal to 1 by phi squared, is equal to 2 minus phi is equal to 3 minus root 5 by 2 and is 0.38. This is in radians units. To get it in degrees, we say gamma is equal to 2 pi phi inverse squared, which is approximately 2 pi into 0.382, and the answer becomes 2.4 radians. So that was just a fraction. We needed to still convert in terms of degrees. It is 60 degrees into 5 minus 2, which is approximately 137.51 degrees. You could say approximately 138 degrees. This is the crux of the idea of Phyllotaxis patterns, because the divergence angle alpha that we dealt with at the very beginning, which is given as the number of organs per turn by the number of turns, for most spiral phyllotaxis is 0.385 turns, and that is 138.5 degrees. So it becomes apparent that botanical and mathematical patterns are intimately related. If we follow a geometric model, which can be called a toy model, then we can answer what is the basis of this. In this, we need another term, few other terms to be defined. That alpha we are familiar with, the divergence angle. The growth index, which arises from the Phyllotaxis meristem and its growth. Sort of what we saw earlier. The Phyllotaxis meristem growth depends on the R, which is radius of the central zone, Z, V, which is the centrifugal velocity of organs moving away from the center due to growth. So as the growth expansion happens, there is movement outwards. This is what is referred to as centrifugal velocity. And T, which is the time between the appearance of two primordia. By definition, V times T is equal to the distance traveled by one new primordium during one plastic run. One plastic run is one expansion cycle of appearance of a new primordium. The growth index then can finally be written as G is equal to V T by R. Please note that this is dimensionless, as we are now dividing length by length. It is a characteristic of a certain growth regime. A toy geometric model can show that if G and alpha are independent variables, we can generate classic families of Fibonacci spirals, both clockwise and counterclockwise. This is the insight of a group of physicists working in active matter and pattern formation. This model doesn't completely explain everything, because in nature, while alpha varies, but Fibonacci series still appear. In other words, the patterns are robust. The solution suggested by Uder and Duadi is that alpha and G are not independent. And this requires more mathematical analysis, which is beyond the scope of this current study. I'm only going to leave you with one quick view of their paper because it reveals something about what we have been talking. So these are the spirals they obtained by changing the value of alpha. Now up to here, there's no spiral, it's just spikes. You start getting a smaller and smaller alphas around 0.4 something. And for a fixed alpha, when t is changed, you start seeing structures that appear to look Phyllotaxis like. The additional analysis involves this coupled model, which we will not deal with today. That's it for now, and we conclude the atom formation segment.